All right, Tyler, welcome to the pod.
Hey, thanks for having me, Packy. Good to see you both.
We're going to kick it off. I'm going to ask what you think the pie of energy sources in the US looks like in the year 2050.
It's a good one and a challenging one. By most studies, we're going to need about 80% of our energy by 2050 to be from a clean source if we want to meet our climate goals. And I think regardless of how you break that apart, it's going to be a combination of wind, solar, nuclear, and other clean energy sources. And look, you see John Kerry the other day at a conference where he stated that even if we quintuple the amount of renewable energy over the coming decades, we're still on track for a 2.4 degree increase by 2050, which does not meet the goals that we need. And you have a similar IEA report that states that we made it increase nuclear by 2 to 8 times over the coming decades if we want to meet our goals. So I think ultimately it is going to be a mix of energy. It's going to depend on nations around the world. In the US, I think you could see it grow from where we're at 10% today to 20% and upwards in the future to meet the goals that we have by 2050. Of course, the X factor here is fusion. And there's a lot of exciting work going on in fusion, a swarm of activity, amazing companies that are raising a lot of capital and have exciting milestones coming up. And I do think that is one of the X factors that could change how that's going to look in the next 30 years.
Well, Tyler, I'm really excited to get a different angle on this nuclear energy topic that we are doing for the show here. Maybe talk to us a little bit about how you got into nuclear energy, but specifically, how did you start thinking about nuclear in space?
Yeah, it is a very kind of roundabout early story. And I was a sophomore at Vanderbilt University in Nashville, Tennessee, computer science major, thought that I was going to go work at Google, Facebook, Amazon, you name it. And the beginning of my sophomore year, I was talking to a friend of mine who interned at United Airlines the previous summer. And he was talking about this summer at United, he really started to notice the reliance of the aviation industry on oil. And this was back in 2017. You were starting to see some conversations about electric airplanes, but at the time, really a lot of decarbonization of transportation across the board. And electric airplanes are great. Batteries don't necessarily have the high power density for long endurance flight. So we got together a couple weeks later and said, how else could you power an airplane? And for some reason, he was a human and organizational development major. I was a computer science major. We said, what if you put a nuclear reactor on a Boeing 777 and you could build this long endurance, clean energy aircraft that could, totally radicalize the aviation industry? So very random. It's an awful idea for so many reasons, but we ended up getting in touch with a professor at Vanderbilt who guided us and mentored us for a couple months and shared with us that in the 1950s, the US government spent over $1 billion trying to build a nuclear-powered airplane. And at a couple points, we actually had critical reactors on airplanes flying over the US. In the early 60s, Kennedy canceled the program, but this professor said, it's been 60 years. Why don't you all dig into this a little more? So that was our first foray into nuclear and looking at nuclear reactors on Boeing 777s. My friend that I mentioned, Jonathan, and I ended up then getting in touch with a graduate student at Vanderbilt who was working on a similar concept, except instead of using nuclear reactors, looking at radioisotope power systems, compact devices that convert the heat from decaying isotopes into electricity, boxes the size of microwave ovens that generate electricity for decades, and looking at this technology on an unmanned aerial vehicle. So looking at powering drones for long endurances. To kind of cut the story short, we ended up looking at radioisotope-powered drones. Once and for all, in the summer of 2018, recognized we should just not mix nuclear and aviation, but more broadly noticed this issue of access to energy in these off-grid regions, from the surface of the moon to on orbit to the Arctic to the seabed, and seeing that radioisotope power systems could have a lot of usability in these domains commercially built in the coming decades. So a very roundabout story of how we got from a nuclear-powered Boeing 777 to building radioisotope power systems for use on the moon, on the seabed, and many other environments.
We're doing this season on terrestrial nuclear energy, but what's going on with the nuclear in space? I saw that NASA is going to be doing something with nuclear in space. What's the state of nukes in space in the year 2023?
Yeah, it's an incredibly exciting time and really the most exciting time for the nuclear space industry since really the 1950s and 60s. And I think that there's a lot of similarities to the terrestrial nuclear market in that sense. Kind of the very brief history of nuclear power in space. So the first use of nuclear power in space was in 1961 when the US launched a radioisotope power system into space. In 1965, the US launched our first reactor. And through the 20th century, both the US and the Soviet Union launched hundreds of nuclear power systems into space for powering satellites, for powering assets on the moon, for powering deep space nodes, and a lot of our greatest scientific accomplishments in space, from Voyager, Cassini to Mars rovers, have all been powered by nuclear. And you're really seeing this, renaissance in the space right now. And similar to what I think you see in the terrestrial nuclear industry, but also similar to the aerospace industry in the early 2000s, this is being commercially led now. And that is a distinct difference compared to previous decades in the use of nuclear power in space. And you have unbelievably exciting activity, everything from developing nuclear reactors to power settlements on the moon, to nuclear reactors for thermal propulsion and electric propulsion for satellites, to radioisotope power systems for powering landers and rovers on the moon, to highly maneuverable satellites. And you have a wide range of activity from, again, very small power systems to large power systems, everything from maneuverable satellites to landers on the moon to deep space probes to bringing humans to Mars in the coming decades.
Can you talk to us, Tyler, a little bit about the difference between radioisotope power and, let's say, nuclear power for propulsion?
Yeah, absolutely. So there's really two core ways that nuclear is used in space right now, as mentioned. And that's radioisotope power systems and fission reactors. And radioisotope power systems are hot rocks in a box. You have these isotopes that are decaying over decades because they're unstable. And as they decay, they produce heat. So you have these rocks that are just generating heat over decades as they decay based on the half-life of the isotope. So for example, the isotope that we're primarily using is called strontium-90. And strontium-90 has a half-life of roughly 30 years. So over the course of 30 years, you're getting relatively constant heat generated. You can then convert that heat into electricity, and again, have a small box the size of a microwave oven that generates electricity for decades. Now, this is small power. We're talking tens, hundreds of watts of electricity. On the other hand, you have the use of nuclear reactors in space, and same core physics as nuclear reactors on Earth. You have uranium, hit it with a neutron, it fissions, you get a chain reaction, you get heat, you convert that heat into electricity. A lot of the reactors being developed right now for space, though, are smaller. We're talking tens to hundreds of kilowatts of electricity, some ambitions in the future to get to the megawatt scale. So kind of the two forms to generate electricity. And then there are multiple ways to use nuclear energy in space, primarily focused on propulsion or power. So we'll talk about power first, and let's focus on the lunar surface, an environment where there's a lot of interest of nuclear energy right now. And, as a part of the Artemis program, NASA and a lot of our international partners are going back to the moon, and not just to visit the moon, but to stay there this time. And this is also huge commercial activity in this area, again, kind of following the same trend of commercial industry working in the space and nuclear industry and taking the charge in a lot of those fronts. But when you are on the moon, you're generally in lightness for 14 days and darkness for 14 days, based off of the way that the moon orbits the Earth and the Earth orbits the sun. So if you're only using solar power and batteries, it can be very challenging, if not impossible, to operate in those 14-day lunar nights. For example, the US is going to land 2 landers on the moon later this year, built by commercial companies that are likely going to operate for 14 days and then freeze to death. With a radioisotope power system or other sources of nuclear, you can have heat and power that enables these assets to operate for years instead of 14 days. Really critical as we look to have this sustainable presence on the lunar surface. As we look at future settlements as well, nuclear reactors, of course, are a great source of power, given a lot of the dark and shadowed regions on the lunar surface. So that's kind of that focus on power and specifically on the lunar surface. And I'll add that there's only one asset on the surface of the moon right now that is operating 24/7, 365. And that is a Chinese rover that is powered by a radioisotope power system using plutonium from Russia. So a lot of what we're doing and contracts we just won from NASA and our engagement with other commercial companies is to build American-made assets that can have that same presence on the lunar surface. So that's kind of the power piece. The other side is propulsion. And there's really 2 ways to generate thrust using nuclear as a source. And that is nuclear thermal propulsion and nuclear electric propulsion. Nuclear thermal propulsion being using the heat from a nuclear reactor to heat up hydrogen. You get really hot gas, and the gas creates thrust as it's ejected from the nozzle. And you can build a really fast rocket. And there's a lot of interest in the military for very high thrust, high delta V satellites using nuclear thermal propulsion. There's also a lot of focus on seeing how we can cut the transit time to Mars so that we can bring humans there faster and increase the likelihood of safe human visits to Mars. So that's NTP, nuclear thermal propulsion. The other flavor is nuclear electric propulsion, which is using the electricity from a nuclear reactor to generate thrust through an ion drive or an ion thrust. And this is generally lower thrust, but much longer endurances. So if you want a slow, long burn, that's a great use for nuclear electric propulsion. So, a lot of really exciting work there going on. You have programs at DARPA and NASA called the Draco program, focused on nuclear thermal propulsion. You have a program out of Air Force Research Laboratory called JETSONS, focused on nuclear electric propulsion. And at Zeno, we have contracts in both of these areas. We have a contract with the Space Force to combine our technology with electric propulsion to develop a highly maneuverable small satellite targeting a launch in 2025 or 2026. And as of July, we also have a contract with NASA working with Blue Origin Intuitive Machines to provide power on the lunar surface to enable their assets to operate and survive during the lunar night and operate for longer than 14 days.
You anticipated our next question, but I'd love to just even hear a little bit more about Zeno, how you started it. We've talked to a bunch of founders in nuclear, and there's this like very clear pattern that it's you start a software company, you make a bunch of money, and then you go into nuclear. You seem to have skipped the first step. So like, how do you decide to take the research in college and start this thing? And like, what's the company look like today?
Like a lot of things, I think it was just curiosity in college. And I give a lot of credit to Vanderbilt for developing and fostering this culture where we were encouraged to just wander and think and be curious. And again, started off with this nuclear powered airplane. And, Zeno really came together in the summer of 2018. And this was when we got a $50,000 grant from the National Science Foundation through what's called the I-Corps program. And this is funding not to do technology development, but customer discovery. Before you invest a lot of time and capital into building a company, ensure that you're actually solving a problem in the marketplace. So over the summer of 2018, we did like 120 interviews with folks ranging from 4-star generals in the Air Force to executives at Lockheed Martin and Boeing to just energy executives, and heard really for once and for all that, again, we should just not mix nuclear and aviation. But as I mentioned earlier, more broadly notice this issue of access to energy in these off-grid regions, from the moon to the seabed, these regions of growing importance in the coming decades because of budding commercial activity, because of renewed great power competition. And we started looking at radioisotope power systems, again, a technology with a rich history. Over 1,000 radioisotope power systems have been built historically, used both in space and also terrestrially. And there's really two flavors of this technology that's been used before. And that is using the fuel strontium-90 or the fuel plutonium-238. And plutonium-238 is historically what's always been used in space. Again, Voyager, Cassini, Mars rovers. And it's a terrific isotope, a long half-life, great thermal properties. It's an alpha emitter, so it's easy to shield. It can also be a complex isotope to produce. So the US right now is producing enough fuel to power marquee NASA missions. But again, as we start to see the growth of operations, there is just not enough plutonium to power the missions that could use a technology like this. On the other hand, you have strontium-90. Strontium-90 being much more of an abundant, available material, one of the largest byproducts of nuclear reactors, really a nuclear waste material. And because of this, over 1,000 strontium-90 radioisotope power systems have been built before. But historically, strontium-90 has required massive amounts of shielding. So the systems were really heavy and had no usability in space. So I give all that background to say that Zeno really kind of started on these dual set of hypotheses that there was this need for reliable, long endurance power as we see growing activity in these off-grid environments from the surface of the moon to the seabed to the Arctic. And that B, if we could build a radioisotope power system that is affordable, but also lightweight, so that's a key combination that would open up much broader usability. And our approach here is using strontium-90, this available, abundant fuel form, with a novel design that allows us to use far less heavy shielding material, resulting in a more lightweight heat source, enabling for the first time a commercially built radioisotope power system using an available, abundant fuel in a lightweight form factor, opening up much broader usability in a variety of these environments.
That's great. You mentioned a few things here. You mentioned cost, right? Novel design. We've talked a lot about these topics with our terrestrial nuclear guests. We've talked about economics, we talked about regulation, even some of like the cultural elements around nuclear, like the environmentalist anti-nuke movement. Yeah. What did these three topics look like for nuclear in space? Like, is there regulation and the economics? Like, what does that all look like?
Yeah, I'll start with cost and economics because it's a big distinction compared to terrestrial markets. And when you look at nuclear terrestrially, at the end of the day, what matters more than anything else is the dollar per kilowatt hour. These are primarily competitive energy markets. And you are starting to see this change a little bit. You look at X Energy, for example, who is now looking to use the heat, in the chemical industry. And you're starting to see where there's use of industrial heat. But, generally, you want to get your energy cost as low as possible, or else you could get outcompeted by other energy sources. In space, it's a very different paradigm, and it's not about the cost of the energy produced from nuclear. It is about the capability that is enabled, and it's enabling brand new capabilities, from taking a lander that right now can operate for 14 days and enabling it to survive for 5 years and operate on the lunar surface. This is taking satellites that are in static orbits right now and increasing the maneuverability of them so they can have more dynamic operations as space becomes a contested environment. This is about cutting the transit time to Mars so we can reduce the radiation that astronauts are receiving to, again, increase the likelihood that they can safely visit and return from Mars. So again, it's not about the cost. It's about the capability that is enabled. And I'll give another example to put some newer numbers on this. Right now, the rule of thumb price to land 1 kilogram on the surface of the moon is $1 million. So you have a lot of companies right now that are commercially landing payloads on the lunar surface for a price of around $1 million. And that $1 million will result in 14 days of operations. Now, if we can tell someone who wants a scientific payload or commercial payload on the lunar surface, this can operate for 5 years instead of 14 days. Again, that completely blows up the economics there. It's a brand new capability. And we're still working through what this business model is going to look like exactly with a lot of these providers. But again, a very different paradigm than terrestrially, where the cost of energy is extremely competitive and one of the primary drivers. Regulatory is in a very exciting area for space nuclear right now. And in 2019, there was a presidential memorandum that overhauled the launch approval process for spacecraft with nuclear power systems. And prior to this presidential memorandum, any spacecraft with a nuclear power system, whether it had a gram or 1,000 kilograms of nuclear material, had to go through the same multi-year, multi-agency safety review that ended in the president's signature. And very notably, only the government could launch nuclear power systems into space. This presidential memorandum did two things. First, it is breaking down the launch approval process into 3 tiers based off of the risk level of the launch. Tier 3 being the highest risk launch, primarily a highly enriched uranium reactor. Tier 1 being the lowest risk launch, primarily a radioisotope source that meets certain standards to ensure that it will be safely launched. And these tiered approaches, again, have different tiers of regulation surrounding it. Tier 1, for example, being able to be regulated and authorized for launch by a single agency, whether that is NASA or the Department of the Air Force. So it broke this down into potentially a more streamlined process. Second, for the first time, this presidential memorandum opened up a commercial pathway to launching a spacecraft with a nuclear power system under the jurisdiction of the Department of Transportation and the FAA. So in a lot of ways, this was the presidential memorandum that has now unleashed this wave of commercial space nuclear companies and commercial space nuclear opportunities. So right now, with our contract that we have with the Space Force, we're working diligently, meeting these guidelines at a presidential memorandum. We're engaged with the FAA and the Department of Defense. Very excitingly, we've developed an approach, and we submitted this approach to the FAA in January of this year, and our payload review application was accepted, which means the FAA believes that there could be a chance to see this to actually approving a launch. And right now, we're targeting an approval for the launch in early 2025 to enable our launch in the latter part of that year into early 26, which could be the first commercial nuclear power system ever launched into space, hopefully when we execute against that.
Thanks for listening so far. Hang on, we'll be right back after a quick word from our sponsors. Age of Miracles is sponsored by my longtime partners and friends at SecureFrame, the only compliance automation platform with AI capabilities that helps customers speed up cloud remediation and security questionnaires. One of the things I love about SecureFrame is that it takes this annoying thing that every company has to do in order to unlock revenue from other companies and makes it easy and simple. SecureFrame empowers businesses to build trust with customers by simplifying information security and compliance through AI and automation, not wasteful human hours. By automating manual tasks related to security, risk, and compliance, SecureFrame allows companies to focus on growing their business, the thing that they're there to do. That's why thousands of fast-growing businesses, including AngelList, Ramp, Remote, and Coda, trust SecureFrame to expedite their compliance journey for security and privacy standards such as SOC 2, ISO 27001, PCI DSS, HIPAA, GDPR, and more. Trust me, if there's an acronym that your company dreads, I bet SecureFrame can help. And I recommend it to all of my portfolio companies. So if you're listening and you don't want to deal with all of those forms and you want to let SecureFrame handle it for you, sign up for a free demo at secureframe.com and mention Age of Miracles during your demo to get 20% off your first year of SecureFrame. This episode of Age of Miracles is brought to you by Tegus, the go-to research destination for bold investing. Investors are always on the lookout for the companies who will disrupt the status quo. So why stick with vendors who are unwilling to innovate? Tegus is opening up a whole new world for investors. It gives you access to new data, proprietary data, AI, and technology that no other company in the world has. With its unified platform, you can combine fragmented workflows under one roof and compete on your ability to analyze companies, not on how well you aggregate data. The impossible is the new normal. Learn more and start your free trial at tegus.com/miracles.
Amazing, Tyler. What do you make of the FAA being the regulatory body? Obviously, they've mostly focused on airplanes. Do you think this is the right body for regulating our paths in and out of space, or should there be something else?
No, I do think it is good. And the FAA has been taking a very good approach at this right now. They are still reviewing these payload review applications on a case by case basis while they're working out what their final guideline is going to be. But the FAA has a rich history of approving space launches. So I do think that it is a very good fit for the commercial space nuclear launches. And they also are working closely with what they're calling an INSERB, an Interagency Safety Review Board. So this brings in folks from NASA, from the Department of Defense, from the Department of Energy, from the NRC to provide guidance as needed in support of approving these launches.
That's great to hear.
Yeah, I would love to hear about how you think about the competitive dynamics in the market. The fact that you can make this happen at all is unbelievable. There are buyers out there right now. Things are good. But thinking about this as a company, like 5 years down the line, you make this work. How does the market evolve? How do you think about protecting your place in it? Walk me through being a startup in this industry.
It's an interesting industry to be a startup. We frequently say that, Facebook coined the phrase move fast and break things. And you cannot do that in the nuclear industry. You certainly can't do that in the nuclear space industry. So, we like to say that we move fast and bend things. You can only bend things so many times, and you can only go so far in pushing the status quo. And because of that, I do think that makes it a little more difficult to have this pure advantage of the speed of a startup company that you have in potentially pure software or other fields. If you're in a software company, your pitch to investors or others is we are simply going to move faster. While we do believe that we can move quicker than a lot of large players, again, I don't think there is that exact same advantage. So what we have been focusing on, recognizing that competition is already starting to come up and is only going to grow in the future, we believe that we are doing really well. Sure, we have our IP, we believe we have some protection because of that. But we're really building excellence in every category of not just building things on paper, but building hardware in real life. So this is great engineers that not just know how to build on paper, build hardware. This is focusing on our supply chain of access to fuel and facilities. This is working through the regulatory process. This is ensuring that we have a great quality program. So assuring that across the board, we have areas of strength. And that is going to allow us to execute. And you look in the nuclear industry, the aerospace industry, execution across the board is relatively quite poor. And I think that is really the competitive advantage that we are looking to develop, is a company that states goals, that meets these goals and executes against them. And with the contracts that we now have from Space Force, from NASA, and some other folks, we now have this unique position to execute, be the first company to launch this power system in space, ideally on the surface of the moon. I believe that will give us a good competitive advantage as competition certainly begins to grow in the coming decades. But, I think this is also a market that is growing quickly. There's a lot of opportunity for a lot of companies to play in here. This is certainly a growing pie. So, it is not a zero-sum game by any means. So we're excited about a lot of interest in a lot of the companies that are starting to work in this area.
So Tyler, what's the hardest thing about building radioisotope power systems for space? Is it something about the actual hardware you're building? Is it related to launch? Is it regulatory? Is it something else? Like, what's your number one, biggest challenge?
Right now, and it kind of follows what I just said before, and I think it's what we're starting to do really well, but it is execution. It is across the board from ensuring that our design is in a place that it needs to be, that we have access to the fuel that we need. We have access to nuclear facilities. We're working through our regulatory approvals with the FAA and the Department of Defense, that we're hiring at a pace that we need to, ensuring that all of these aspects of our company are moving forward in sync to ensure that we can execute on the work that we have. So, it's a little bit of a cop-out answer that it's not one specific area. But, I do think compared to, for example, a lot of these advanced nuclear reactors, our technology is, all things considered, relatively simple on hot rocks in a box. We're using fuel that exists today. We're using facilities that exist today. There is some novelty in the regulatory environment, but we believe that we have a good hand on it and that we're working towards that. So it is not necessarily, that there is this one massive area that is this huge hurdle to overcome. At this point, in a lot of ways, it is on us to execute against the work that we have and to actually deliver this technology to customers, on the timeline that we promised.
You mentioned hiring here. What types of people do you need to bring on to your company, particularly on the engineering side, to actually build your first product?
Yeah, I was actually just talking to our VP of Engineering, Lindsay Bowles, who joined us last April from TerraPower, which is, of course, an amazing company. I was talking to her yesterday about this, that most of our engineering team actually is coming from the aerospace industry. Certainly have a good group of folks that are from the nuclear industry, but when you look at what is required into thermal analysis, structural analysis, systems engineering, a lot of that, of course, carries over into people who have background in the aerospace industry. So again, certainly we have our nuclear engineers, we have our chemists, our radiochemists, structural analysis, thermal, mechanical systems, certainly a diverse group of engineers that are on the team. But yeah, I would say mostly coming from the aerospace field. But beyond just an engineering team, again, I do think we've put just as much focus and emphasis on building a really strong supply chain team, a really strong regulatory team, a really strong business development and government relations team, a really strong people and operations and team to ensure that we have a cohesive and exciting culture that people love to be a part of. I think that we've had a lot of emphasis on growing strong teams, in each of these business units, not necessarily just focusing on engineering.
I'd love to dive in on what some of the potential business models might be at scale, or like just the different ways that you're thinking about actually making money on this business. Because it is crazy that there is like a business that is going to be providing power to lunar rovers, but you also are a business. And so like, what does that look like?
Yeah, I would say there's kind of three flavors of business models we've had conversations about. First is, very simply just a direct sale. You buy the power system for X hours. You can now have your lander operate for 5 years instead of 14 days, or your satellite can now be, more maneuverable with electric propulsion. So, just a direct sale. And, this is kind of the precedent that we are setting with a lot of our current government contracts. The second is looking more at a power as a service type model, where a customer is buying the power over the time that it is being generated. So, there will be potentially an upfront fee, and then you buy power over the 5 years that you want to power your lander on the surface of the moon. And the last model is kind of a more creative one. It's really because of this fact that we are enabling capabilities. And this is looking at where we can actually capture some of the upstream value of what we're actually providing. So capturing some of the upstream value of the entire satellite, of the lander that is now operating for far longer time periods. Given again that this is not just buying electricity so that you can power villages, power cities, power industrial equipment, or enabling brand new capabilities that no other power source can do. So looking where there can be more strategic arrangements to actually capture some of that upstream value instead of just selling the power system or selling the power from it.
That's cool. And in the power as a service model, is it technologically possible to, if someone stops paying their bills, to just turn off their power from Earth?
No, that is, one of the good and, sometimes challenging things of radioisotope powered systems is this is just the physics of radioisotope decay. These things are just always producing heat. There is no way to stop it. So that is a good question of if someone stops paying, what exactly to do about that? But no, not exactly a way to turn it off.
Makes sense. We won't put this part in so that your partners don't figure that out. But in terms of financing this business, obviously there are the government contracts. I would imagine you're talking to venture capitalists. Like, what do you think the right capital mix for this business is, kind of over time?
Yeah, we certainly, as I think a lot of nuclear companies are doing, and a lot of aerospace companies are looking at this mix of government funding and private capital. And right now we're at a ratio that is staying at roughly 1-to-1 between our government and private capital. Right now we're a little heavy on the government. Hopefully soon we'll be more heavier on the private capital. Certainly looking at both of these to develop this technology. And I think a very key thing about this is from the early days, we set a goal for what products we want to develop by what time period. And we have then seen the best way to capitalize this product development in a combination of government funding and private capital. And I think one of the challenges you see a lot of companies deal with is that, especially in the government space, they start chasing these opportunities because people are throwing money at them, these shiny objects. And it can very easily distract you from the course of the product that you want to build, the product that you believe has the largest market potential in both the government and the commercial place. So, we have tried to be diligent, and we certainly have brought on some contracts that are maybe, not quite on this line, but tried to be diligent that the contracts we're executing against in the government space are helping us develop a technology that we see broad use for, yes, the government, but also commercial industry, so that by 2025, we can have multiple products in different markets with a combination of government and private capital that has gotten us there, that we can then start scaling production to meet the demand in both of these markets, in space and terrestrially, soon afterwards.
What do you see as some of the biggest risks for the business for Zeno Power? What are you most worried about?
not to beat the dead horse, but it's execution and following that scaling. In a lot of ways, we have de-risked a lot of aspects of the company, from our core technology to our supply chain. We're working through the regulatory environment. At this point is executing and delivering on these contracts that we have. And then probably most importantly, and where I think the biggest challenge is scaling on the back end of that. Nuclear companies do not build things at scale historically or today. So I think that, certainly that is another shift in the paradigm. What we're trying to do is to build modular systems that we can build at scale, build a nuclear battery factory so that we can deliver these to the wide set of customers that we see today and that we expect in the future. So I think that is where a lot of the challenges is going to be. This is building out the robust fuel supply chain, building out or acquiring or adapting this facility so that it can really produce at scale with the throughput that we need. Again, that is just a challenge that nuclear companies are currently working to tackle, but have not necessarily tackled yet. And we certainly have an easier bout here than nuclear reactor companies, again, just by the general simplicity of our technology. But, really scaling in the latter part of the decade is, I think one of the largest challenges that we have remaining.
Yeah. And you mentioned supply chain. How did you go about de-risking the supply chain, and how much does your supply chain look like the supply chain of, let's say, a terrestrial microreactor?
So very, very different. Of course, most terrestrial microreactors are looking to use HALEU, and there's a lot of great work from the Department of Energy and industry to develop this HALEU supply chain, but HALEU is not developed at scale today. Meanwhile, the isotope that we are using it because it exists today separated as a waste product. We're really taking a kind of a crawl, walk, run approach here at building this in step, working in tandem with the Department of Energy, with different industry folks to really fulfill this vision of taking what right now is this nuclear waste product that is abundant, that is a liability to the Department of Energy and industry, and reusing it as a power source to enable space exploration, to support national security missions, to support the clean energy transition in these off-grid environments.
Great.
One thing that I wanted to maybe get clear on is, like, when you say rock in a box, like, what does the technology look like? Like, what does the product look like? Do you have to like set a fuse and like kick off the decay process? Is that just happening and you're grabbing it and putting it in a box and that's it? Like, what does the product look like in the process of putting it together look like?
As I mentioned, this fuel exists today all around, producing heat right now in pools and storage, just sitting there producing heat. We take it, we process it, and we press it into our heat sources, which are, think of soda can sized heat sources that are just generating heat for years at a time. And there actually is some usability in just heat sources. There's a product that's historically been built that we are as well, called radioisotope heater units, that just provide heat. Some of these space vehicles and landers on the moon, may just need heat to operate in these dark regions. But for our core products, we take these heat sources and then you surround it by an object that converts this heat into electricity. And there's two mechanisms that we are using and we're developing to convert this heat into electricity. And that is thermoelectric generators and Stirling engines. And thermoelectric generators use the Seebeck effect to take the difference in temperature of the interior from the heat source and the ambient environment. You get a flow of electrons, the Seebeck effect, you get electricity. These are solid state devices, zero moving pieces, extremely reliable. This is what has been used for Voyager, Cassini, the Mars rovers. But you convert about 5% of that heat into electricity. So relatively low efficiency, and you have a lot of excess heat that you need to reject in these different environments, which can be challenging in space. So that's kind of this first product, known as an RTG, a radioisotope thermoelectric generator, where you have the heat source, you have the thermoelectrics, you have a heat rejection system to reject that excess heat into space, and that is your RTG. You can look up a picture. Generally, the ones that have been used have kind of these cylinders with fins on the outside, again, roughly the size of a microwave oven. We are also working to develop an energy conversion system with some of our partners called a Stirling engine, which is a dynamic system that uses moving pieces, a free piston, but you can get efficiencies of 20, 25, maybe even 30% of conversion of this heat into electricity. So much higher efficiency, but it does come with moving pieces, which does potentially decrease the reliability in certain uses. So we're developing both of these right now, this thermoelectric system, no moving pieces, extremely reliable but lower efficiency, and a Stirling engine, which has moving pieces, dynamic but higher efficiency. And NASA contract, again, that we were just awarded in July, it's specifically focused on this radioisotope Stirling generator using this more efficient energy conversion for use on the lunar surface. And this is an area that NASA has been working for years in the development of Stirling engines. China actually earlier this year just flew the first Stirling engine into space. So this is another area where there's a lot of focus for a variety of geopolitical reasons as well.
The geopolitical topic has come up a few times now. It seems like kind of the great power conflict here is one of these catalysts for the space. What percentage of the market do you think that will be over the next 10, 20 years? Is it majority of the market, or will we really see truly like on their own commercial markets develop?
So look, our hope and vision is that a truly commercial marketplace does begin to exist in the cislunar environment in deep space. Certainly, you're starting to see a commercial marketplace develop, orbiting the Earth, and we see a lot of opportunity there as well. But a lot of these near-term uses, whether we are selling directly to the government or we are selling to a customer that at the end of the day is getting their funding from the government, a lot of it is focused around geopolitics and really this race back to the moon. You look a couple weeks ago, NASA Administrator Bill Nelson stated for the first time publicly that we are in a space race with China for the South Pole of the moon. You look over the last couple weeks and you had Russia, India, Japan all send landers to the moon. You have the US sending multiple later this year. You have hundreds of manifest missions to the lunar surface, not just in the US, but internationally over the coming decade. And, certainly geopolitics is driving that. And, that is a large focus, again, of why we want to not just go to the moon and leave, but go there and stay there. And nuclear can be, and we believe will be, a critical part of having that sustained presence on the lunar surface.
It's a funny risk to the business that it feels just so certain at this point that we're going to be spending a lot of money trying to win the moon, win space generally. This is another kind of dumb leading question for the audience here, maybe as much as me, but what's the value of winning the South Pole of the moon or being on the moon or beating China to the moon? Before it was like a technological capability thing and a fight against the Soviets and a bunch of good stuff came out of it. But why are all these countries spending so much money on the moon now?
Well, I think let's first talk about why the South Pole of the moon. And in the South Pole of the moon, there are what's called permanently shadowed regions. And these are these craters that, as exactly the name makes you think, never see sunlight. So these are dark at all times. And in these dark craters, we have belief that there's a lot of ice, that there are other minerals that could be used. Ice, of course, becomes water to feed humans. It also can be used as a propellant for future space missions. And it's a great launching pad potentially to Mars and beyond. So if you look throughout history of what has driven conquests, it's primarily focused on resources. That is why people have explored. That is why people want to go and command areas of land. So I think that ultimately it is the resources on the moon and the South Pole of the moon that is driving people back there. And then you also look at it that whoever visits a place first is generally the one that has some ownership over it. And that is the moral guidelines. That is the culture that encompasses that domain. And I think that you look at the US and the Artemis partners, they want to see the US and its Artemis partners, a lot of the Western world, be the one that is setting a lot of the precedents of the sustainable use of the lunar surface and the resources that, might and hopefully will exist there.
Great. Packy, I was going to head towards our closing question. Well, one thing we love to ask our guests, I'm going to expand this now to the universe. What does it look like in a universe where we have abundant energy?
It's again a great question, and I think it's very different in space than terrestrially. And that is because in most areas of space, you have a lot of solar power. Yes, there are these niche uses of during the lunar night, in these permanently shadowed regions, in eclipses around Earth where solar doesn't work. But I think it is less about abundance in space, and it is more about these capabilities that can be enabled by the heat, the electricity, and the high power density of nuclear energy in space. This is what is going to enable us to have sustained presences on the lunar surface, whether these are unmanned rovers or settlements on the surface of the moon. This is what is going to enable more dynamic space operations with greater maneuverability, given the high power density of nuclear energy in space and the continuous power from it. This is what is going to cut transit times to Mars to ensure, once again, that astronauts can safely go there and return. So I think it is less about this abundance of energy. It is about these capabilities that can be enabled by nuclear energy in space that will support national security missions, will support scientific missions, will support commercial missions, and ultimately, I believe, be critical in driving humans to be interplanetary species, and both with settlements on the moon, in the future Mars, and beyond.
Awesome. Tyler, this was a fascinating conversation. We really appreciate you coming on.
Of course, this was fun. Glad we could do it.
Yeah, thanks so much, Tyler. It was great. I learned a ton.